Now, let's find the Laplace transformation of a trigonometric function, specifically cos of at. Applying the standard definition of the Laplace transformation, we start by rewriting the expression accordingly. Now, we see that the integrand involves the exponential and the trigonometric function. At this point, we have a couple of options. We can use tabular integration, or we can apply Euler's formula. The Euler's formula states e power iota theta is equal to cos of theta plus iota sine of theta. To rewrite this in form of at, we can write e power iota at equals to cos at plus iota sine at. Now you can notice that it is cos of 80, which is the real part of this Euler's identity. So we can rewrite this as the real part of e power iota at equals to cos 80. Now substituting this part here, we are going to be getting the integrand in exponential form. Now, just like we did in the previous example, we take the negative sign common here. We are going to be adding both of these because the bases are the same, that is exponents. So the powers are going to be added. The negative sign will be taken common here because e power negative infinity yields 0. And after integration, when we'll be applying the upper limit, and if it is positive, then e power positive infinity is equal to infinity, which would diverge, and that is something we want to avoid. So, taking negative sign as common, we can rewrite this integrand. We integrate the exponential expression and rewrite everything accordingly. Exponent as base here, this in the box. Differentiation of the box equals to minus s minus iota a. So, minus s minus iota a, multiply and divide. This is the real part here. E power negative infinity is 0, so this entire expression is going to become 0. E power 0 becomes 1, so we are going to be rewriting this expression as don't forget, there is a real part written outside. Now, if we observe the denominator, it is s minus iota a, which is a complex number. To simplify this, we will multiply the numerator and denominator by a complex conjugate, meaning s plus iota a divided by s plus iota a. So we get this. Since we are interested in the real part of the result, because there's a real part that has been coming along ever since we applied the Euler's identity, we will be just taking this, which is s divided by s squared plus a squared. Now, if we were taking the Laplace transformation of a sine function, then if we go above, we would have chosen the e power iota theta equal to cos of theta plus iota sine of theta. Since we were interested in sine of theta, we would have taken this part, meaning that we would have rewritten this expression as imaginary e power iota theta equals to sine of theta. So eventually in the result, we would have imaginary here instead of real, and we would have taken iota a divided by s squared plus a squared. We would have ignored the iota sign. To summarize this, the Laplace transformation of the cosine is going to be s divided by s squared plus a squared. And since it was real written here, we only took the real part. However, if we were taking the Laplace transformation of the sine function, then we would have imaginary written over here. And eventually we would have only taken a divided by s squared plus a squared, which is the imaginary part of this equation. Now, let's move on to finding the Laplace transformation of hyperbolic trigonometric functions. Let's take cos h of at as our example here and find its Laplace transformation. Applying the definition of the Laplace transform, we begin by rewriting the expression accordingly. You can see over here that we're dealing with an exponential function multiplied by a hyperbolic trigonometric function. So just like we did for cosine, we will convert the hyperbolic function into its exponential form. Now we know the identities for the hyperbolic functions. The cos h of at is equal to e power at plus e power minus at divided by 2. And for sine hyperbolic function, it was e power at minus e power minus at divided by 2. So using this one, the identity for cos hyperbolic function, we substitute it into our original expression and rewrite the integral accordingly. Since the exponential terms have the same base, we can add all of these powers. So taking this outside the integral sign, we can rewrite this expression as this. Now you'll see that this breaks down into two separate Laplace transforms. One is going to be for the e power positive at, and the other is going to be for e power negative at. So we are going to rewrite this as this. From our earlier examples, we know that the Laplace transform of e power at is going to be 1 divided by s minus a. And similarly, for e power minus at is going to be 1 divided by s plus a. So to simplify this and rewrite it, now I'm going to simplify this and add these two together by using the method I refer to as my method. So it is going to be like this. This 2 and this 2 is going to cancel out. This is going to be giving us our final answer as this, s divided by s squared minus a. Now, to point out the obvious difference, we can see that for the trigonometric functions, the denominator has positive sign, while for the hyperbolic trigonometric functions, the denominator has a negative sign. This is what I mean. The Laplace transformation of cos at is equal to s divided by s squared plus a squared, whereas the Laplace transform of the cos of hyperbolic function is s divided by s squared minus a squared. So just remember, the sign in the denominator is what distinguishes the trigonometric case from the hyperbolic one.